In 1973, Black-Scholes gave the world a formula. It assumed one number for volatility, constant, fixed, unchanging, and from that single assumption, derived a closed-form price for every European option. For 14 years, that assumption was roughly serviceable. Then, October 19, 1987 happened, and as we established in Episode 4, the volatility surface never returned to flat. Out-of-the-money puts began carrying permanently elevated implied volatility relative to at-the-money options. The skew appeared and stayed. The field needed a model that could generate a non-flat, skewed surface, not by fitting a curve to it after the fact, but by building a process for volatility that would naturally produce one. That model arrived 6 years later in a 1993 paper published in the Review of Financial Studies by Stephen L. Heston, then at Yale University. The Black-Scholes model is built on a single stochastic differential equation. The price of the asset follows a geometric Brownian motion. The model works beautifully under normal conditions, but it has one fundamental blind spot. It cannot reproduce a volatility skew. If sigma is constant across all strikes and maturities, then by construction, every option priced with this formula will produce the same implied volatility. The surface will always be flat. The model cannot do otherwise. The problem Heston identified was not that Black-Scholes was wrong about the math. The problem was that one of its inputs, volatility, was not constant in the real world. It clustered. It mean reverted. It was correlated with the price itself. And it had its own randomness. Heston's 1993 paper, A Closed-Form Solution for Options with Stochastic Volatility with Applications to Bond and Currency Options, set out to address 3 specific observable features of real markets that Black-Scholes could not accommodate. These 3 features are not theoretical abstractions. They are measurable properties of historical data. Volatility clustering can be verified in SPX return time series. Mean reversion is visible in any long-run chart of the VIX. The leverage effect, the tendency for the S&P 500 to move inversely with implied volatility, has been confirmed and quantified across decades of high-frequency data, with the bias-corrected leverage effect estimate for SPX running approximately negative 0.76 to negative 0.78 in empirical studies using tick data, Ait Sahalia, Fan and Lee 2013, Wang and Mikeland 2014. Heston's solution was to add a second stochastic differential equation, one that describes not just how the asset price moves, but how its variance moves alongside it. The 2 equations are coupled. Each affects the other through a correlation parameter. The Heston model introduces 5 parameters beyond the risk-free rate and initial asset price. Each has a specific interpretable role in shaping the implied volatility surface. There is one boundary condition that matters for the variance process, the Feller condition. It comes from the boundary behavior of the square root process used in the CIR model, and it states the practical significance. When Feller is violated, variance can touch 0 in simulation, so the boundary behavior matters. In a 2025 review of Heston parameter sets used in the literature, one SP500 return example has kappa as small as 0.013, implying a variance shock half-life of about 53 days. This is not a failure of the model in the pricing sense. Option prices computed via the characteristic function can still be valid. But it is a documented property practitioners should be aware of. Of the 5 parameters, one has a uniquely direct effect on the shape of the volatility skew, the correlation RO between the price Brownian motion and the variance Brownian motion. The intuition is this: when RO is negative, a downward move in price, DS0, is correlated with an upward move in variance, DV0. This means, when the market falls, volatility tends to rise. From the perspective of an options trader, this means that the out-of-the-money puts, which pay off precisely when the market falls, are being priced in a world where those scenarios are accompanied by elevated volatility. Higher volatility means higher option prices. Out-of-the-money puts become more expensive relative to the Black-Scholes flat surface prediction. The skew emerges directly from the correlation. This is not a curve-fitting trick. It is a mechanistic consequence of the model's structure. When you write down 2 correlated Brownian motions and price an option using the resulting joint distribution, the skew is a mathematical output of the correlation sign. Published equity index option calibrations consistently show a negative RHO, and SPX-specific leverage effect estimates are strongly negative. Across equity index examples, RHO often falls in the range of roughly negative 0.5 to negative 0.8. This is consistent with the observed downside skew in index options and with the empirically documented leverage effect. The long-run variance theta, when square-rooted, gives the model's long-run variance anchor. Calibrated values of theta between 0.06 and 0.10 correspond to a long-run volatility anchor of roughly 24 to 32%. That is above the historical VIX long-run average around 19 to 20, which is plausible because option implied variance embeds a volatility risk premium. The Black-Scholes model's greatest practical advantage was not its accuracy. It was the fact that it produced a closed-form equation you could compute in seconds. When Heston proposed adding a second stochastic process, the first question was, does this still produce something tractable enough to use in practice? Heston's key contribution was to show that, even with stochastic variance, a semi-closed form solution exists. Not a simple formula like Black-Scholes, but an analytical expression involving a single numerical integral that can be computed rapidly. The solution uses the characteristic function of the log price under the risk-neutral measure. The option price itself is recovered by numerically integrating the characteristic function, a single one-dimensional integral that modern computers evaluate in milliseconds. This is why the Heston model became a practical industry standard. It is almost as fast to evaluate as Black-Scholes, yet it produces non-flat surfaces. To make this concrete, using one published equity index calibration example from the LSQ nonlinear study, kappa, chart 118, theta, chart 0.067, chi, chart 0.575, RHO, chart negative 0.667, V0, 0.027, with S0, chart 100, K, chart 90, T, average 0.5 years, R, chart 0.01, and pricing a 6-month out-of-the-money put. This illustrates the practical difference. Black-Scholes requires you to manually feed it a different sigma for each strike. An ad hoc correction. Heston produces the price variation across strikes automatically from its 5 parameters. The market practitioner calibrates the 5 parameters once, then reprices any option in milliseconds. The most illuminating way to understand the Heston model is to animate each parameter independently, starting from a baseline surface and varying one parameter at a time while holding the others fixed. This is what every quant does when first implementing the model. The Heston model succeeds in producing non-flat volatility surfaces from a principled mathematical structure. It captures the 3 features identified in segment 1, clustering through mean reversion, persistence through kappa, and the leverage effect through RHO. It produces reasonable skew and term structure for medium to long maturity options. And critically, it is fast enough to calibrate and reprice in real time, which is why it became and remains the industry benchmark for equity and FX options pricing. For medium maturity options, say 1 to 12 months to expiry, empirical studies and calibration examples show that Heston errors can be manageable in liquid equity index markets. The exact error level depends on dataset, weighting scheme, optimizer, and whether prices or implied volatilities are used as the calibration target. The most consistently documented limitation of the standard Heston model is its behavior at short maturities, options expiring in days to a few weeks. The model cannot produce a steep enough smile for short-dated options. The technical reason: in the Heston model, the variance process needs time to diffuse and generate the spread of volatility outcomes that underlies the smile. At very short maturities, the variance has not had time to deviate significantly from V0. The resulting short-dated smile is nearly flat, much flatter than what markets actually price. This was formally analyzed in the small-time Heston smile literature, including Ford, Jacquier, and Lee's work on the small-time smile and term structure of implied volatility. The stationary Heston model, developed from the stationary process idea of Pages and Pan-Loup and applied to Heston by Lemaire, Montes, and Pages, addresses this by initializing variance from its invariant distribution rather than a deterministic V0E, producing a steeper short-dated smile. But the standard Heston remains insufficient for very short maturities. The broad pattern is consistent with both the theory and practitioner backtests. Heston is most useful in ordinary liquid regimes, then becomes less reliable when the surface is dominated by jumps, event risk, extreme short-end convexity, or fast regime shifts. A 2025 practitioner SPY backtest makes the same qualitative point, but it should be treated as practitioner evidence rather than a peer-reviewed benchmark. Preston, 2025, medium, where Heston breaks. The documented limitations of the base Heston model have spawned a large family of extensions used in practice. The most common are jumps in the price process, Bates Model 1996, which adds a Poisson jump component to the asset price SDE, time-dependent parameters to better fit the full-term structure, and rough volatility models, L. Usch and Rosenbaum 2016, which replaced the CIR variance process with a fractional Brownian motion, allowing the model to capture short-time smile explosion rates that the standard Heston cannot. We have built the Heston model. We understand its 5 parameters, we can watch the surface respond to each one, and we have been honest about where it fails. But there is a question we have not asked yet. If every practitioner knows that implied volatility systematically overprices realized volatility, if the volatility risk premium is a documented, persistent, and quantifiable gap, then who sells that premium? What instruments let you trade the level of volatility directly without the directional exposure of an options position? The answer is the variance swap. Episode 6. This video is for educational purposes only. Nothing in this video constitutes financial advice, investment advice, or a recommendation to buy or sell any security or derivative instrument. The Heston model and all analytical frameworks discussed here are tools for understanding options pricing and volatility dynamics. They are not forecasts of future market behavior, and they do not predict future option prices or returns. All data and numerical figures are drawn from published peer-reviewed academic research and public sources. Option pricing models are approximations of market behavior. Always conduct your own independent research and consult a qualified financial professional before making any investment decision.